Hello my friends and welcome back to the You Can Do TV channel. The new Conci Barrage integrates modern equipment to reinforce and control a historic weir system. This work reshapes the headworks through a sequence of coordinated operations, each designed to strengthen control across upstream and downstream conditions. That blend of old alignment and new hardware already feels like a serious upgrade. Site preparation establishes cofferdams and excavation boundaries before heavy equipment takes over. Vibrohammer operations follow, driving sheet piles along the planned perimeter to the required depth. Using ICE 815C vibratory hammers paired with 600 pp power packs, centrifugal force and vibration frequency are tuned to penetrate dense layers while maintaining alignment. Those piles slide down with a confidence that leaves little room for hesitation. The upstream cofferdam forms a stable enclosure, allowing dry work conditions for the main weir and auxiliary structures. Formwork installation moves next, with Quarry systems set up for structural concrete works at the new Conci Barrage. Designed specifically for the job, the jack-operated formwork enables fast setup and removal with reduced manpower. Everything locks together so cleanly, it almost feels pre-planned to the last detail. Concrete placement follows defined stages, keeping geometry consistent across large sections of the barrage. Material delivery intensifies once the super swinger and concrete pump are deployed. The Rotex super swinger extends reach across wide pores, delivering aggregates and concrete with controlled placement. High output rates allow large volumes to be placed efficiently, minimizing delays between lifts. That boom reach covers ground faster than most setups twice its size. Remote control operation further streamlines coordination on site. Spanning a deep fjord isn't just about crossing water, it's about redefining movement across western Norway. The Hardanger Bridge project, delivered by Statens Vegvesen, unfolds as a long sequence of structural decisions rather than a single build. Each segment added here carries consequences far beyond its own weight, and that pressure is real the moment the formwork rises. Work advances section by section along the curved span, where formwork units are lifted, adjusted, and temporarily supported before concrete placement. Hydraulic jacks raise each formwork section into position, a task that can take close to an hour per lift. That pause isn't downtime, it's a checkpoint. Engineers confirm alignment before reinforcement continues, especially where the bridge width must be extended and additional steel is required to handle load changes. Concrete placement follows once checks are cleared. Test samples are taken on-site to confirm the delivered mix matches specifications. No shortcuts here, the fjord doesn't forgive weak concrete. Consistency across pores matters, because differences can accumulate over long spans. Each pore must reach consistent density and bonding, because every completed segment becomes the foundation for the next one. In tighter areas near crossbeam sections, adjustments are made before the process returns to more standardized construction. As sections advance outward, steel wire installation progresses in parallel. When tensioning is complete, a final protective layer is applied to shield the cables from long-term exposure. That coating might look quiet, but it's doing years of work already. Cable protection plays a direct role in maintaining structural performance. Meanwhile, teams operate both high on the pylons and down in temporary barracks, coordinating lifts, pours, and inspections across the site. One curved span becomes a symbolic turning point, marking a transition toward completion. Wait, this is the moment everyone remembers. This section visually confirms that the full crossing is finally within reach. With the last structural elements secured, the bridge moves from a worksite to a landmark. The fjord, once a traffic bottleneck, opens up as if a cork has been pulled free. Celebrations follow, but the real achievement lies beneath the surface. Every measured lift, tested pour, and reinforced section holding the line together. That's not just a crossing, that's commitment cast in concrete and steel. "4 feet of concrete doesn't sound dramatic until it's poured beneath an active airport terminal in Salt Lake City. This moment centers on the terminal tunnel mat slab at the new SLC terminal, a structural base designed to carry future terminal loads without compromise. That scale alone already hints at how little room there is for hesitation here. Before any concrete arrives, crews prepare the tunnel foundation, reinforcing the area to support a continuous slab rather than segmented sections. 2 concrete pump trucks are positioned to maintain steady placement, while logistics teams coordinate an uninterrupted flow of delivery trucks. Miss one timing window, and the entire sequence starts leaning the wrong way. The pour itself unfolds over roughly 8 hours, supplying about 700 cubic yards of concrete into a 4-foot-thick mat slab. Placement follows a controlled pattern to distribute material evenly and avoid internal stress points. It's one of those situations where speed helps, but control decides everything. As layers rise, surface leveling and internal consolidation keep the slab uniform across the tunnel footprint. Crews monitor depth, alignment, and consistency in real time, adjusting pump output and placement routes as conditions shift. At this point, the slab feels less like wet material and more like a moving deadline. Once placement is complete, finishing teams stabilize the surface to prepare for curing. The slab must settle as a single structural unit, capable of supporting the tunnel and the terminal systems above it. Hard to blink knowing what will eventually sit on top of this. This terminal tunnel mat slab pour marks a key milestone in the new SLC terminal redevelopment program. It's the kind of work that disappears from sight later, yet carries everything that follows. Staying dry below ground depends on how one liquid layer is applied with intent. Illbruck OS 925 liquid waterproofing forms a seamless barrier for underground building sections without primers. Applied by brush or trowel, its bitumen latex base spreads evenly and resists sagging. This stuff behaves more like paste than liquid. Reinforcement mesh can be embedded. Then a second coat follows after drying. 3 days later, joints simply don't exist.
See rails welded and stressed in close succession when the Pandrol CD500 works with a mobile flash butt welder at Rosenquist. Instead of locking rails and returning later, this setup handles stressing right after welding, keeping crews moving. That shift alone cuts long idle windows that usually stall rail work. Rails are aligned and welded on site using the flash butt unit, forming a continuous rail string ready for stressing. The CD500 clamps onto the rail and applies controlled force to reach required stress under real track conditions. Temporary anchors aren't needed, simplifying layout along active corridors. Seeing welding and stressing stay this close feels unusually efficient. Operators track temperature data and rail length while the machine maintains tension automatically. Adjustments happen in place without releasing the rail, reducing repeat handling. This avoids the back and forth that normally eats up possession time. The compact form fits limited clearances common on busy lines. It's the kind of setup that makes night shifts end earlier than expected. Once target stress is reached, fastenings are secured, and the section is cleared for traffic. Road building depends on a long chain of machines working in sequence, and this journey begins deep inside a limestone quarry in central Kentucky. A hydraulic rotary drill drives downward into solid rock, boring precise holes that prepare the face for controlled blasting. Explosive charges fracture the rock into shot material that can be handled by heavy equipment. That first break already decides how smoothly everything else will run. Loaders move in to gather the blasted stone, feeding it into off-road dump trucks. Each truck carries roughly 51 tons per load, hauling the material toward the primary crusher. These trucks travel short but demanding routes, repeating the same cycle all day. Haul distance inside the quarry strongly influences fuel use and cycle timing. Seeing the same loop repeated shows how volume matters more than speed here. At the crusher, the rock drops into a jaw system that reduces large fragments into manageable pieces. Instead of forcing uniformity immediately, the crusher creates a controlled range of sizes suitable for downstream handling. Jaw settings determine how much stress is passed on to screening equipment further along the line. In underground operations, a similar routine follows blasting, with additional machines scraping loose material from tunnel walls to maintain stability. This step quietly decides whether the site stays workable or turns risky. Crushed rock moves outward, often by conveyor, emerging at the surface into a surge pile. This pile acts as a buffer, keeping the plant running even if one section pauses. Surge capacity helps prevent interruptions from rippling across the entire system. From there, aggregates pass over a scalping screen that removes oversized material for recrushing. Smaller stones continue across finishing screens that divide them by size. Those vibrating screens are doing more sorting than most people realize. Radial conveyors stack the aggregate into smaller mounds, limiting segregation within each pile. This matters later, when consistency affects how the road performs under traffic. Stacking patterns influence how evenly material flows during loading. Quality control follows, using sample piles drawn directly from stock. A sorter divides material into test portions. Samples are dried and measured for properties like gradation and specific gravity. Skipping this stage would gamble, with every mile laid afterward. Prepared aggregate becomes the foundation of the roadway. A base course is spread across the roadbed, forming the structural layer beneath the surface. Base thickness controls how loads are distributed into the ground. At the asphalt plant, different aggregate sizes are loaded into cold feed bins. Computer-controlled gates release exact proportions onto a conveyor, feeding the drum mixer. Liquid asphalt arrives by barge, rail, or truck and waits in heated tanks. This is where stone stops acting like stone. Hot mix asphalt is stored in heated silos, then discharged into dump trucks bound for the job site. Weight limits shape every load, especially on Kentucky highways. At the site, paving machines place the asphalt smoothly across the prepared base. Rollers compact the mat, locking everything together. Compaction levels determine how well the surface resists deformation under traffic. That final pass decides whether the road lasts years or just seasons. Within minutes, the surface is ready for traffic, completing a process that turns raw rock into working infrastructure.
Power on this scale exists for one reason: to rebuild what lies far below the surface at Lake Hope Dam in New Plymouth, Ohio. DeWind one-pass trenching brings the MT-4500 to the site, a machine built to cut and reinforce ground in a single continuous movement, designed for depths other equipment simply cannot reach. That torque figure suddenly makes sense when the ground barely resists. Before cutting advances, operators position the MT-4500 along the dam alignment, setting the path for a straight, uninterrupted trench. The cutting system engages as the machine moves forward, driving downward through layered soil to nearly 70 feet, maintaining wall stability while excavation continues. That steady forward push feels like controlled force refusing to slow down. As material is removed, DeWind's proprietary soil mixture is introduced directly into the trench. This blend combines with the native ground to form a dense underground barrier, engineered to block seepage beneath the dam. The key here is timing. Excavation and mixing occur together, preventing collapse and eliminating the need for staged passes. You wouldn't expect a single pass to handle this much depth so cleanly. The MT-4500's powertrain delivers 4 500 horsepower and over 1.5 million pound-feet of torque, allowing the cutting head to maintain consistent performance even at extreme depths. No pause, no retreat. Movement remains continuous as the reinforced wall takes shape below ground. That depth number alone could catch anyone off guard. Throughout the run, alignment and depth are constantly monitored, ensuring the underground wall stays uniform beneath the dam structure. Once the trench line is complete, the surface shows little hint of the reinforced barrier, now locking the foundation in place. Hard not to think this machine treats 70 feet like a warm-up. The Lake Hope Dam repair relies on this single, uninterrupted operation to secure long-term stability, using strength applied exactly where it matters. Spanning hundreds of kilometers across Queensland, the Australia Pacific LNG pipeline links coal seam gas fields to the export terminal at Curtis Island. This project advances through terrain that demands coordination between land access, materials flow, and controlled welding sequences. That length alone changes how every decision gets made. Route preparation establishes access tracks and trench lines before pipe delivery moves in. High-pressure steel pipe sections arrive staged by diameter, supporting both 42-inch and 36-inch lines. Alignment crews position each section while welding teams complete field joints under strict inspection. Those welds carry a lot more responsibility than they look. Once joined, the pipeline is lowered into the trench, maintaining curvature limits and protective coatings. Padding and backfill secure the line, restoring ground profiles across farmland and crossings. Seeing the land return to normal so quickly feels unexpected. Compressor and valve stations integrate control points along the route, allowing pressure management and isolation when required. Testing follows with hydrostatic checks to confirm integrity over long distances. That pressure test decides whether months of work move forward. The finished pipeline connects southeast Queensland gas fields to liquefaction facilities offshore. Hard not to think of this as an underground highway built for energy. The Australia Pacific LNG pipeline stands as a coordinated system designed for long-term transport under demanding conditions. How can a bridge extend across open space without building temporary support below? This incremental launching simulation in Portugal shows how the deck advances step by step, relying on controlled movement rather than ground-based falsework. The concept centers on building the superstructure behind the abutment, then pushing it forward in measured stages. That forward slide looks calm, but the forces involved are anything but small. Construction preparation focuses on the casting yard, where bridge segments are formed in a fixed position. Each segment matches the final deck profile, allowing alignment to stay consistent as new sections are added. Once a segment reaches strength, hydraulic jacks apply force to move the entire deck forward along sliding bearings. Seeing the whole structure move together still feels unreal the first time. As the deck advances, temporary bearings guide its path, reducing friction while controlling direction and elevation. The nose structure at the front lowers bending stress as the deck crosses each pier. That slender nose doing the heavy lifting says a lot about smart engineering. After reaching a pier, the deck settles onto permanent supports, locking position before the next launch cycle begins. Segment after segment, the bridge grows outward in a controlled rhythm defined by load balance and alignment checks. You'd never guess the deck is carrying its own weight across gaps this wide. The incremental launching method limits work at height, reduces site disruption, and allows repeatable construction control. This simulation highlights how coordination between structure design and movement strategy makes long-span crossings possible without building from below. Two towers rising from the Izmit Gulf connect Dilovasi to Hersek-Burnu as the Osmangazi Bridge takes shape across open water. Foundation work moves below sea level where steel piles are driven to strengthen the seabed under each tower. Caissons are produced in dry and wet docks, then positioned with tight coordination. Hundreds of piles quietly decide whether everything above will stay steady. Deck sections are joined piece by piece across 682 meters. Seeing land finally meet land hits harder than expected. Two chimney stacks in the boiler house at Ferrybridge C power station stand moments away from removal as Keltbray prepares a single controlled blowdown in West Yorkshire. Structural links are released, supports give way, and gravity takes over in sequence. This kind of timing leaves no room for hesitation. One misstep here rewrites the whole site plan. Tunnel excavation at the Yusufeli project moves forward under steep terrain, where access and alignment matter as much as speed. Survey marks guide the heading and drilling rig's position holes for controlled blasting that opens the rock face section by section. Clear alignment at this stage reduces corrective work deeper inside the tunnel. Every advance here feels earned, not rushed. After detonation, loose material is cleared to restore visibility and allow the next cycle to continue. Clean removal keeps the working face readable for the next technical decisions. Progress resumes with mechanical support tasks that stabilize the ground before deeper penetration. Rock bolts are drilled and installed to lock fractured layers together, followed by additional drilling for drainage and pressure relief. Bolt spacing and depth directly influence how loads transfer into the surrounding rock mass. Injection work reinforces weak zones by filling voids behind the face, limiting future deformation. Steel supports are then erected as part of the temporary lining system, forming a rigid frame against surrounding stress. Once these frames are in place, movement around the face becomes more predictable. Mesh is laid across the surface to bind sprayed material evenly and prevent localized failure. Geological face mapping records visible layers, fractures, and changes in rock behavior, guiding adjustments in support density. These observations help match reinforcement levels to actual ground response, not assumptions. Shotcrete is applied in controlled passes, sealing the surface and forming a continuous shell that maintains tunnel geometry. Uniform thickness here plays a major role in long-term stability. Each round follows the same sequence, even though ground conditions rarely behave the same way twice. Tunnel boring and auxiliary machines return to position once stabilization is verified, pushing the heading forward under controlled force. Equipment coordination tightens as depth increases, with ventilation, spoil removal, and access handled together. Smooth coordination prevents idle time in confined space operations. Advance rates are monitored to balance safety and schedule without stressing the surrounding rock. Final lining work begins after the excavation reaches its designed length. Reinforcement and formwork prepare the tunnel for permanent concrete, locking geometry and strength into place for decades. This final shell carries long-term loads rather than temporary construction forces. The Yusufeli tunnel transitions from exposed rock to a finished underground structure built for demanding geological conditions. Each completed section reflects a layered sequence of blasting, support, analysis, and finishing carried out in strict order. Consistent cement quality at Sarbottom's cement factory depends on how raw materials are processed, checked, and refined through controlled industrial stages. Limestone, additives, and corrective materials move through crushing and proportioning before entering grinding systems supplied by F.L. Smith. Material balance at this point decides whether later adjustments stay minimal or escalate quickly. The ground mix feeds kiln operations, where thermal conditions drive chemical bonding that defines clinker strength. This is the stage where shortcuts simply don't survive quality checks. Clinker then cools and transfers to finish grinding through crossbar, pulley-driven systems that stabilize load and speed. Smooth transfer here keeps particle distribution within target limits. Cement types are developed by blending clinker with materials such as pozzolana or ground granulated blast furnace slag. PPC, OPC, and PSC emerge from controlled ratios rather than guesswork. Changing one percentage shifts performance in real construction conditions. Quality control teams run continuous checks using X-ray diffraction machines to verify mineral composition. Lab data here speaks louder than production targets. Any deviation triggers immediate correction upstream. That moment when numbers align feels like quiet relief across the floor. Packaging and dispatch follow only after consistency is confirmed across batches. You can sense the confidence once every test aligns. Bottom Cement's process stays grounded in verification, not assumption, ensuring each bag performs the same after it leaves the factory.
The final RE330 contact wire draw moves across the NBS Wendlingen-Ulm line, with rail power systems deploying the Zeg-Montage-Einheit to close out 80 kilometers of catenary. Operators and machines advance together from Hohenstadt toward Ulm, guiding the wire through the catenary while tension stays stable. The Zeg-Montage-Einheit manages feed and pull so alignment remains consistent. That steady pull keeps sag within limits and protects pantograph contact. Section by section, droppers and messenger connections are completed, locking geometry before the train moves on. Progress stacks up fast when 80 kilometers are scheduled, yet the convoy keeps pace. Seeing the line extend non-stop feels like watching distance shrink. Checks follow each run to confirm height, stagger, and continuity before the next stretch. Adjustments are handled on the move, avoiding delays while keeping parameters within target. August 2021 marked the last pass, closing lots 4 to 6 with the draw completed. Finishing the last pole lands with a quiet punch. The result is a continuous contact system ready for reliable high-speed operation between Wendlingen and Ulm. Powerhouse earth excavation progresses at PLTA Poso Satu in Pomona, Poso, setting the base for 435 MW units. Excavators cut stable benches, trucks clear spoil, and crews check slopes before deeper cuts continue. Safety checks guide every pass. Progress stays strictly sequenced. This groundwork decides everything later. Feels tense seeing the pit open this wide. PlastiRoute 2-component cold plastic drives spotline structure marking with Gaveco equipment on trafficked highways. Paste-like material mixes with a peroxide initiator, curing without solvent as machines lay consistent lines. UCME drop-on glass beads follow to secure wet night visibility. This combination keeps markings readable under pressure. Equipment pacing controls width and texture through trafficked zones. Seeing beads lock in feels reassuring. The result supports Type 2 road markings built for highways. A 4-day schedule drives ACI's box culvert install, balancing cranes, joints, and backfill in sequence. Day 1 sets excavation limits and base prep, keeping grades aligned for rapid placement. That alignment decides everything later. Cranes lower culvert sections, joints seal, and backfill follows in measured lifts. Traffic windows stay short. Seeing sections lock together feels decisive. Compaction and headwalls close gaps, restoring flow paths. Final grading ties shoulders back to the roadway. No wasted motion here. Time-lapse compresses effort, but coordination carries the load. Across crews, sequencing stays unforgiving today. A chip and seal crew renews pavement grip using binder spray, stone spread, and rolling passes. Trucks, spray binder, stone follows, rollers lock it down. That pace matters. Traffic returns quickly. Feels like flipping a switch. Cleanup seals edges, leaving a tough surface. Cost stays controlled. Crews finish before weather shifts.
A mega swing installation lets road semi-trailers roll onto rail without changing their structure. This loading method focuses on movement efficiency rather than forcing trailers to adapt to rail equipment. A standard semi-trailer enters the terminal and aligns with the railway wagon. Instead of lifting vertically, Megaswing rotates the loading platform sideways, bringing the wagon to the trailer's level. That single rotation removes the size limits pocket wagons struggle with. Once aligned, the trailer rolls directly onto the wagon under controlled guidance. Locking points secure the wheels and frame, stabilizing the load for rail travel. No special trailer design, no reinforced frames required. The system accepts road trailers already operating across Europe. After securing, the platform swings back, restoring the wagon to its travel position.
Heavy equipment for mining and construction demands consistency long before it reaches a job site, and Dresta machines are built around that expectation. At Crosland Technica, production focuses on tractors, front loaders, pipe layers, and motor graders designed to work under sustained load without losing control. This is the kind of manufacturing that favors repeatability over shortcuts. Every model follows a structured flow that keeps variation in check, while allowing different configurations to move through the same system. Material preparation sets the pace. Structural steel components are cut, formed, and matched to each machine frame, ensuring dimensional accuracy across batches. Welded assemblies move forward only after alignment and strength checks confirm they meet design requirements. Skipping alignment here would echo through the entire build, and nobody wants to chase problems later. Consistent geometry at this stage keeps downstream assembly predictable instead of corrective. Frames then advance toward component integration without unnecessary stops. Uniform frame interfaces allow shared tooling across different machine types. This uniformity helps maintain steady throughput without retooling delays. Powertrain installation anchors the next stage. Engines, transmissions, and driveline elements are positioned to balance output and durability. Mounting points are reinforced to handle vibration and torque during extended operation. You can tell this stage decides whether a machine feels solid or just assembled. Once secured, these systems are connected to cooling and exhaust layouts, sized for heavy-duty cycles. Correct placement here supports load transfer without overstressing surrounding structures. Hydraulic systems follow, defining how each Dresta machine works in the field. Pumps, valves, and hoses are routed to support precise control of blades, buckets, or pipe handling arms. Pressure testing verifies stability across operating ranges. Hydraulics don't forgive guesswork, and this step proves it. Clean routing also reduces service complexity once the machine leaves the factory. Access paths around major connections reflect real maintenance practices, rather than ideal conditions. Operator stations come next, shaping daily interaction between human and machine. Cabs are installed with attention to visibility, access, and control layout. Electrical systems integrate displays, controls, and safety features into a unified interface. This is where long shifts are either supported or quietly punished. Comfort here directly affects productivity outside the factory. Clear cab layouts reduce operator hesitation during repetitive field tasks. Final assembly brings together body panels, attachments, and finishing components specific to tractors, loaders, pipe layers, or motor graders. Each machine then enters inspection, where functional checks confirm coordinated movement and response. Seeing every function respond in sequence feels oddly reassuring without needing drama. Adjustments remain measured, aimed at consistency rather than speed. Before delivery, machines undergo operational testing to confirm readiness for mining and construction environments. When Team Orion batteries unleash current on the track, that power traces back to one of the most controlled manufacturing lines in the industry. Production starts with chemical preparation, ensuring each formula delivers the right conductivity and stability. Electrodes are coated through chemical deposition, rolled, and then cut into exact dimensions. Separator films are prepared before cell assembly begins under constant control and sampling. Once sealed, each cell is filled with electrolyte in a 0% humidity chamber. That's a space no air dares to dry out further. Contact tabs are installed, cells activated and matched for capacity. The wiring, case assembly, and labeling give each pack its identity before packaging. Hard case construction and laser-welded tabs show how much performance depends on structure, not just chemistry. When these batteries power RC cars on the track, you see what engineering under total control can achieve: fast, fierce, and flawlessly consistent NN. How does a steel coil transform into angular and square profiles without cracking? Scrap metal is loaded into the furnace at Corporación Aceros de Guatemala, where it is melted into a uniform molten mass. The intense heat removes impurities and prepares the steel for rolling into high-quality AG profiles. The raw metal flows like liquid power, ready to be transformed. Once molten, it is poured into molds to create slabs, which are later reheated and fed into the rolling lines. Steel slabs then enter the high-speed rolling lines, destined to become a variety of AG profiles, including square, round, angle, and flat bars. Each slab is inspected for surface consistency, thickness, and alignment before encountering the rollers. The way these slabs glide under pressure yet retain perfect form is impressive. Operators ensure the feed is perfectly centered, preventing deviations during shaping. The first stage of shaping involves heavy rollers compressing the steel into preliminary profile shapes. As the metal passes through successive rolls, it gradually acquires precise dimensions. You can almost feel the momentum in every turn of the cylinder. Sensors monitor the width and thickness, and any variation triggers an immediate halt to prevent defects. That tension looks stronger than you'd expect for a mid-size line. Once the steel reaches the target profile, it advances to cooling and sizing stations, where exact measurements are confirmed again. Workers manually verify samples to ensure compliance with AG's quality standards. Cutting units then section the continuous profiles to specified lengths, while workers label and sort them for storage or shipping. Quality control is continuous, from rolling to final inspection, ensuring AG products meet the demanding standards of the construction industry. Didn't expect these rollers to shape so many varieties of profiles so consistently. Cutting units then section the continuous profiles to specified lengths, while workers label and sort them for storage or shipping. Quality control is continuous, from rolling to final inspection, ensuring AG products meet the demanding standards of the construction industry. Didn't expect these rollers to shape so many varieties of profiles so consistently. Finally, the profiles are bundled, packaged, and prepared for distribution. Finished products include round bars, square tubes, angular beams, and flat steel sheets, all branded AG. Feels like a symphony of machines and people, each playing its part perfectly. Sometimes it even looks like the steel is performing a choreographed dance, moving in precise harmony with the machinery. That smooth movement of heavy profiles is oddly satisfying to watch. This tightly integrated process reflects both modern technology and the skill of personnel, producing high-quality steel profiles ready for countless applications. Every profile embodies durability, uniformity, and the reliability that AG guarantees to its customers.
Two steps remove all copper from motor stators using the Mr. T machine. Stators ranging from 8 to 30 centimeters in outer diameter are first halved, then fully stripped of internal copper in 2 efficient steps. It's remarkable how such a machine reduces manual labor while keeping operations consistent and fast. The system relies on a hydraulic pump, hydraulic control system, tangential cylinder, pull cylinder, and electronic controls to manage both the cutting and gripping operations. Operators can adjust the reciprocating distance of the blade and gripper, which makes handling different stator sizes feel almost effortless. High wear-resistant hard alloy blades slice through copper cleanly, preventing burrs or material adhesion. Even thick copper coils are removed smoothly, thanks to the synchronized hydraulic system. The automatic thread gripping device further lowers labor intensity during operation. The machine can handle multiple stators in sequence without stopping, which keeps the operation continuous. Once the stator is fully processed, copper is recovered for reuse, while the remaining steel core is separated, supporting both sustainability and efficiency. Seeing the machine handle each stator like a puzzle piece falling into place is oddly satisfying, and the speed at which it works keeps the workflow smooth. By combining hydraulic precision with intelligent mechanical design, the Mr. T machine demonstrates a streamlined solution for motor recycling, making copper recovery faster, cleaner, and safer than traditional manual methods. Operators definitely get a workout, but the machine does the heavy lifting, literally, N.
You can see every step of copper becoming cable through heat, motion, and precision extrusion. Thick copper rods move through the Sanhang cable plant, stripped and drawn into precise strands. To prepare them for insulation, each strand is annealed for flexibility and strength. Polyvinyl chloride is then melted and extruded around the conductors to form a uniform coating. The smoothness of that coating decides how long the cable will last under stress. Cooling water solidifies the PVC instantly, locking it in place. Operators coil the finished lines onto reels, checking diameter and resistance before packing. There's something oddly satisfying about seeing copper vanish under the white layer. Each reel carries the effort of accuracy and consistency essential for power systems worldwide.
Every smartphone starts somewhere, and at OPPO's Chongqing site, the story unfolds in milliseconds. Each phone moves through a chain of high-speed automation, combining digital control with real-time inspection to maintain flawless quality. The surface mount technology (SMT) line applies solder paste onto circuit boards before electronic components are mounted by robotic arms with millimeter accuracy. Then, boards go through download and calibration, setting firmware and optimizing internal parameters. One small misalignment here could mean a dead phone, so automation takes zero chances. Next, fluid dispensing secures key components, followed by camera and battery assembly, where delicate optical sensors and lithium cells are installed. The way those camera modules slide into place almost feels like a trick of timing. Workers add side auxiliary materials, adhesive layers, frames, and seals to reinforce the phone's structure before moving to testing and antenna checks, ensuring perfect signal strength. Optical axis calibration aligns every lens for ideal imaging. Finally, IMEI laminating and inspection confirm device identity and readiness for packaging. By the time each smartphone leaves this line, it's already passed more tests than most gadgets face in a lifetime.
A single copper disc is about to become part of a gutter system, a downspout crafted through the art of metal spinning. The sheet is mounted on a spinning lathe, pressed firmly against a forming mold. As the lathe rotates at high speed, the metal softens slightly from friction and pressure. Step by step, the operator uses a roller to guide and stretch the copper over the mold's surface until it takes its final curved shape. You can almost sense how much control the operator needs to keep the curve smooth and consistent. Kinda satisfying to see a plain disc evolve into something useful for rainwater systems. Finally, the finished downspout section is ready for installation, strong, corrosion-resistant, and elegant in its simplicity. No wonder copper stays the favorite material for traditional roofing work. Copper isn't a metal you'd expect to see turned into a helmet, yet here it's reshaped from flat sheets into a solid, gleaming shell. The process feels both ancient and inventive, showing how patience and precision can bring raw material to life. The artisan doesn't rely on heavy machinery, just hand tools, heat, and instinct. There's something almost poetic about shaping protection out of a decorative metal. Once cut, the pieces are hammered into shape on a solid block. The hammer moves in steady rhythm, bending the copper into domed sections. The metal darkens from impact, gaining a raw, earthy look. Heat treatment follows. The torch brings the copper to a dull red glow, making it soft again for the next round of hammering. The glow under the torch always looks alive, like the metal's breathing. Each strike gives the piece more personality and strength. Sometimes the surface ripples, and he evens it out patiently. Someone in the comments might just say, "That sound of hammer on copper hits different." Two shaped halves are then aligned and held with clamps, ready for brazing. The craftsman uses a torch and filler rod to fuse the seams. The blue flame dances across the joint, melting the rod and bonding the surfaces tightly. It's cool how fire becomes the glue here. Once cooled, the joint turns dark and textured, signs of solid metal work done right. The helmet starts to reveal its full outline, sturdy and balanced. You'd never think copper could look this strong. Then sheets of copper are measured and marked before cutting. The bandsaw slices through the metal smoothly, guided by careful hands. Each piece is sized to fit together later like a puzzle. The edges aren't factory perfect, but they'll be refined as the structure grows. Every curve begins as a rough cut that slowly finds its place. The craftsman seems to anticipate the final shape before a single joint is made. Each copper sheet is repeatedly struck, stretched, and bent, gradually forming the contour needed for the helmet. It almost feels like the copper is being persuaded rather than forced. Once shaped, the sheets are joined together. Careful soldering secures the sections without compromising the metal's integrity. More heat and shaping follow to smooth transitions and fix small gaps. The surface keeps its hammered marks, each one proof of the maker's hand. When the exterior's ready, the inner frame is attached, straps, adjustment rings, and fittings that turn it from sculpture to wearable. He checks the fit, tightens bolts, and wipes away residue. Every joint is checked and adjusted, ensuring the dome, visor, and neck guard come together flawlessly. There's real satisfaction in seeing it go from flat sheet to finished form. The copper now shines with burnt tones and subtle color shifts, showing its journey through flame and force. A piece once lifeless now feels forged with spirit. This kind of craftsmanship doesn't rush. It speaks through every dent and weld.